Good afternoon, everyone, or good morning to some of you might not be here in this time zone and in another side of the world. So my name is Jian Tao, and I'm a assistant professor in the School of Performance, Visualization, and Fine Arts. And today I'm going to teach you all how to get started with the Julian programming language. And this is one of the several short courses offered by High Performance Research Computing at Texas A&M University. And we are offering this through the support from SF, FASTER, MRI project, and also the ACES project. So we have about 5 components for this short course. We all started with FASTER, the machine that you will be using today for practicing and getting started on your job job submission and the Julian exercises. And the part 2, we'll talk about Julian and what and why, and all some basic questions that you might be asking when you get started with the Julian. And part 3 will be about some basics about using Julian as an advanced calculator. If you're familiar with any program languages, these are very basic functionalities any program languages are providing and offering. And thank you for sharing the slides. And also for part 4, we'll talk about some basics of Julian, some basic building blocks for Julian programs. And finally, we'll just give you some examples of how to use Julian to do the plotting. As you can see, we're not covering any advanced features about Julian, about parallel programming and distributed computing and all the other fancy features in the Julian has been really good at. But we hope this short course will serve as an introductory level of course and get you all started. And for those of you who are interested in Julian, probably you'll want to look into some more advanced tutorials on the Julian website or some other places. But we'll be offering some follow-up courses similar to this one in the future. So first, let's get started with the FASTER. This is a machine that we'll be using for exercises. And for those of you who are new to supercomputing centers, and this is one of the machines probably you want to get familiar with, and this will be shared. This is a shared system by the local A&M University researchers, and also shared by the bigger ACES community through the ACES allocation. Through the allocation on the ACES program. So FASTER is kind of different from some traditional HPC systems. It's based on so-called liquid, and you can see it's a company. It's providing high-performance computing solutions for academia, government, and big companies. They have been providing this solution to offer highly composable, high-performance computing hardware, so that you can use Slurm, which is a job management software, or some other software to recompose the hardware in a way that you need it to be. So it's a highly recomposable in a sense. You can request to run the HGPU job, and this HGPU will be put together together with the CPUs requested and memory you need into a virtual computing, I would say, well, virtual computer. You can run your code just like you're running on your local computer, which is dramatically different from the way how the traditional high-performance computing system are working. When you submit a job requesting multiple nodes, and all the nodes are physically separated, and you have to run your get your software working to run your code in a distributed manner. And it's the same here on the programming side, but as far as the hardware itself is configured, it makes it possible for you to put more GPUs than you can do physically in the same node, virtual node here. And you can learn more about FASTER and the hardware information on the our wiki page, and I provide a link on this slide. So FASTER is able to provide you not only GPUs, but also FPGAs and some other computing accelerators, something like IPU, graph core IPU. You can do a quick search about that new architecture, which is different from the traditional computing devices. It also gives you access to high-performance storage pool or the solid-state disks, which is very high performance. And put all this together, you can build your own virtual computing system. And there have been, I believe, 1 or 2 short courses already covering how to use Faster. And you can check out our HPLC website and also get to our YouTube channel and to follow some instruction to get you started on the system. So today we'll give you a very brief introduction about the hardware configuration here, but it's not our primary concern. We just want to get you started with the system. And ACES, which is another big system that HPLC is managing, it's funded by National Science Foundation. And the phase 1 of ACES components are available through Faster. And you can get access to those nodes on Faster as well. So as I mentioned, we have a graph core IPU. You can get, if you get the slides, you can take a look at a graph core IPU, which is a different architecture than some other things you probably haven't seen before. Also, we have Intel FPGAs available. We have 2 of them just for testing purpose. You can try things out if you are using FPGAs for your applications. And also we have Intel Optane SSD, which is also high performance storage system. And you can use it as a memory, which we can greatly expand the way how you do big data applications. So this is the ACES system. It's currently still in the phase 1 stage of this project. For the phase 2, there will be more nodes and more resources available for our users. To get access to HPLC portal, which is a recommended way for you to get started on our systems, we have this website created. I know it's integrated into our existing website. If you get to the portal and click the Faster portal, if you are a local user or Faster portal access, that's if you're from outside Tamu, and you can get to our portal using your access credential. I noticed there was a question here. Thank you, Lisa. So this is for local users. If you get access to the, if you click the button here with a Faster portal, that's what you will see. You'll see this login, and just like a regular credential login, you put in your net ID and your password. You can log in and you can do, you can follow the instructions, get you started. For outside users, you can access our HPLC portal through the access, how to call this, credentials. And then you need to pick your identity provider as access CI. And then you can log in just like your regular access, if you're familiar with that. Otherwise, you probably need to follow the access instructions on their website to get started with a Silog logon. That's a new system. I was a user on Exit, and I spent a bit more time to learn how to use this new system. It's not that complicated. If you follow the instructions, you should be able to get started quickly on that system. So after you follow the instructions, get yourself logged in, and you'll be able to get to the portal. And today, I just want to show you the version that's through a local login. But after you log in, no matter your access user or local user, you'll see the same interface or similar interface. So it shouldn't be a big problem. After you log in, you'll see this cluster. So to slow down a little bit, I'll get to the website so that we all can follow when I'm working on this. So you can click the portal menu here. At the bottom, you have item Faster portal and access portal. So I'll click the Faster portal. This will point me to the portal site. And there are messages of the day, and there are also some other information for the system. And here I think if you zoom in, if you can log in with this with your iPhone and iPad mobile devices. This fluid menu bar can make it easy for you to work on your mobile devices. If you zoom out a little bit, you can see the menus here. What I'm trying to do here, I'll get access to the shell. That's connecting to the shell on the faster node. So this is what I'll see. Depending on your systems, you might have different layout, different size. Currently, I just zoom in a little bit, but you'll see something very similar. So to ask me for my authentication, this is my phone, and okay, now it's actually working on my watch, so I can approve it. Now I'm on. So this is how I can log in with my local credential. I can give it a try with ACES credential. Let me just go back to the website. If you're an external user, you can go to portal and access portal, faster portal. You can log in with your credential. I already have my login information saved. And if I do that, it pointed me to, it pointed me to this, oh, let me try again. So it will be another authentication. Access. Not sure why it's, oh, it's my computer password. Asking me to log in. So you can see it's almost identical, but there's, I believe, when you get to the shell, you can see something very similar because already logging, it's logging into a different front-end node. So for, I believe, someone from HPLC staff team can help clarify. I believe we have login 3 reserved for access users and login 1 and 4 for local users. Is that right? Someone?
Yes.
Okay.
Actually, for the Tamil users, we call it faster 1, faster 2, and the access users, they use a name called a login 3. A little bit different.
Sure. Thank you so much, Zhenhua. So we have, I showed you all how to log in through Access front end and also the Tamu front end. So it's, after logging, your system is the same. It's just like a different, like a namespace. If you're familiar, it's just a different namespace, but it's just the same system we're using. Okay, let me get back to the slides. We can all continue. Okay, so after logging, you input a password, and then you can see the prompt. I'm currently logging this one, the window to the right here. It shows the login from local front end. So you can see the name is a faster 2, and for access users is a login 3. So after you log in, there'll be a bit more work here, but I'll put the slide here, or you can, if you have access to the slide, you can go through a slide or go through the instructions one by one, but I'll get back to the login page, and I'll show you all how I get started. Sorry. So this is the page I log in. Say currently I'm an access user. You can use a clear to clean up the screen, which it's very convenient. Okay, and then what the slides tell us? I need to go back to the slide. First, you want to search, which module is providing Spider. I'm sorry, which module providing Julian. So it's module, I believe Spider, or I'm sorry, it's a Spider. It's a real Spider. It's a difference. I was thinking about something different. Julian. Okay, M-O-D-U-L-E. I'm sorry for my. So when you tap this, and you can get a list of modules that we already provide on our system. we pre-compiled, get everything installed properly. You give this module list. So what you do next, you can do the module load, and you can copy paste. Usually it's good, unless you have very strong preference for some old versions. If you have dependencies in your code you're using, you probably want to pick the particular version. But usually, if you're starting something from scratch, it's good to use the latest version. Usually, it's have all the bugs patched, fixed, etc. So it's recommended to use the latest version. So there is a shortcut called ML, which is a module load. When you type module load, it will print out the module you're currently loading. Okay. And if you want to clean things up, it's module purge. It will clean up everything. If you do that and the module load, there's nothing loaded. You can use up and down key to go back to to run old command, just historical, some command you ran previously, and you can do module load. Now, so another one, you can directly do module Julia, even though it's not recommended, but again, as a new user, you are excused for this kind of mistakes, for this kind of practice. So what it does, so Julia itself is like a shortcut for the latest version of Julia package. So when you do module load Julia, it automatically load the latest version of Julia, which is convenient to get started. But again, when you are trying to develop something in production, make sure you specify the particular version, so then in the future, after the system is updated, you get a new version of Julia installed. When you do the module load Julia directly, you'll get the latest version, which might give you some problems when you're running your code. So after the module load is, after Julia is loaded, you can directly run Julia. So it'll give you the version number and also very nice Julia ASCII art, logo, and you can get started. So that's the very first step. But again, before we do that, there is something I want you all to, before we do anything else, let's go back to the slides, because there are some other things you want to be aware before we move to the next, before we start running anything. So we're all done here. We got Julia started. That's good. If you can see this screen, and that means you're already fully, prepared for the next set of the short course, and we are going to work on it. So some of you might want to try out the latest version of Julia. Currently, it's 1.8.5. You can do it directly. You can download it. You can unzip it, and then you can just directly run it. So before you run it, make sure you do the module purge, so that you are guaranteed that your current version of Julia is not conflicting with any other libraries or the paths or environment variables previously loaded through the module load. So by doing that, you can directly run your own installation. It's perfectly fine. Even though we highly recommend you to use our system installer system, Julia version, which is make it easier for us to help you. If you have any problems, it's straightforward for us to look into the installation and also other log information to see what goes wrong. And if there's any problem, we can help you on that one. But again, this could be used for you to, as an instruction for you to install your own latest version of Julia if you prefer. So these are the things we need to be careful before we start running Julia, mainly because just like Conda, if you're familiar with Python Conda, Conda is installing a lot of packages, especially when doing, I'm not talking about mini Conda. Mini Conda kind of lightweight, but Conda itself is installing a lot of dependencies, a lot of packages in your home directory. If you're not so careful, you can easily use up your quota on your home directory, mainly because you usually have 10, probably 20, 30 gigabytes of quota on your home directory. If you do the direct Julia installation, inside the installation, all the packages will be installed under your home directory .julia. So that's definitely not a recommended practice on high-performance computing systems. So everyone has a limited amount of space allocated for home directory on big machines. The home directory will be copied and backed up regularly. That means, we more or less we need to double allocate your the size of the home directory so that we can keep a copy of what you have. That makes it kind of expensive for us to maintain. for the big systems to maintain. So we usually create a scratch space. You can directly access to the scratch space using $scratch. That's like a environment variable pointing to your own scratch space. With that scratch space, you can store all the installation files or other temporary files. Even it's called a scratch, but we don't clean up scratch automatically, or we whenever you do any purging, anything, we'll definitely let our users know. And you can keep a big chunk of files and data on the scratch space. So here, by setting the Julia deport path to scratch /.julia, you're setting the installation directory of Julian packages and all other documents under the Julia deport path. By doing that, you're leaving out a lot of space on your home directory, which make it easier for the system to managing, and also make it easier for you to switch around working on different projects. So with that said, let's get back to the file, and let's just copy this. That's what I'll do. And we needed to quit the Control D. I'm sorry, let me active. Control D will exit this current shell. So if we currently echo Julia, there's nothing here. So and if you use a tab key, if you should pop up something, but it doesn't pop up anything, that means it's not set yet. So what we do, we export Julia deport path to scratch dot. So when you do the echo Julia, this will point you to the scratch space and you'll be working on. Okay, that's good. That means when I do the installation of all the Julia packages in a second, I'll show you how to do that. It will be installed under this directory. So next we'll do Julia, because let's make sure we have this. Okay, we have the latest version of Julia loaded, so it's great. Now we run Julia. Okay, now we can start installing packages. Since we are not using a lot of external, packages, there are many packages in the Julia, repository. You can download and install those. There are 2 packages that I think we can use for this work, for the exercise today. You can do that using and package command. A quick shortcut is to use this. Let me go back to the slides. And there is one quick shortcut. Is you tap this one, this symbol. It's a right square bracket. Okay, so that's a shortcut. You will learn more about this shortcut throughout this course, which is very neat. So when you tap that, they'll get you to the package installation shell. It's just a prompt, but it's also get all the environment loaded for you. So what do you do? Just add plots. That's one of them. There's another one, I believe. I'm sorry. I believe it's okay. It's called Unicode plots. Let's get this in the. I know this one might not be working here, but let's just get it installed. Unicode plots. Plotly, it's there's another Plotly which definitely will not work on this shell script, but if you have a local installation, it will work for you. But let's install these 2 first. Plots and Unicode plots. Okay, if you do that and then just click enter. Depending on your system, it'll take a while. And you can see some of them missing many because it's a shell here used in the system. It's doing something, but it's not done yet. And you can see it's moving, but you just cannot see the output. It's the web-based shell problem. And sometimes with a different resolution, you might be able to see. Okay, let's just wait. Okay, I'll go back to let it run here. It will finish. I'll go back to the slides. So far you have your Julia deport path exported, which is very important for HPC users, and also get your Julia started. That's pretty good. So I'll leave this slide here for a couple of seconds and let you know in a couple, probably half a minute, so that you know what we are trying to do here. For those of you who are familiar with Linux system, this one is simply get into the directory with a cd $scratch. That's the directory I just mentioned, is scratch space for you. And you can copy the file from the Julia example to the scratch space using copy command. And then you can use a tar unzip and untar this file. And then you can cd that directory. And then you can run a simple example. So this is what I'm going to do next. And I'll switch to my shell prop, but feel free to just check the slides on your end. If you have a link to the PDF file, you can follow, you can copy and paste if you are not familiar with the Linux system. It's still installing, but it's fine. We can open another shell. You can go to interactive, go to the, I'm sorry, this one is Tamu faster, okay. Just want to make sure it's the same. So I can open another shell. You can open as many shells as you want. For example, I can open the third one, the fourth one. They're all active. So it doesn't really matter, you know, even though it's installing for me, it's fine. I just installing in the background. I can just do my work here with another shell. So what I'll do, I'll cd, scratch. And what I'll do next, I'll be copying, I believe, scratch training. You can use a tab to help finish the command, which is also the directory, which makes it pretty convenient. I believe it's Julia example here. That's thank you, Zhenhua. He already copied this under all the scratch space. You can copy to the local directory here. Now you can see this file is under my directory. I can do, let me zoom in a little bit. I can do tar zxvf. Z is unzip, X, oh, I'm sorry, Z, yeah, unzip, X is untar, V is verbose, means you want to print out all the information, F is just print out all the files. So you can do this, it will print out all the files here, you unzipped and untar. It's a directory on the Julia example. So you cd this directory. Now, think about we don't have, let's see if we don't have any module loading. Let's do module load Julia. So do this again. Good. We now have a Julian, so we can Julian hello world. Here we go. So you can get this code executed. So what does this code look like? You can use a VI. Oh no, sorry. If you are not familiar with VI, don't use it. Otherwise, you'll have trouble to quit. So Nano is another one, probably easier for most of users, because there are, you can use a Control X to quit. I'm sorry, not Control X. Is that the? Here we go. Where Control X? Get help. Shift. Okay. No. So I'm a VI user, so I can use VI. I'll show you what it looks like. Okay. Also, you can, sometimes VI might not be working with this web-based shell system, but you can go to the website here. You can go to files. Remember, currently I'm just showing you with my ACES ID, so that's why it shows me the directory here. You can click this directory. It'll point you to the directory. If you go to Julia examples, and you can click this, or you can, on the right side, there's a view, edit, etc. You can use edit here. So this is actually what I have in this file, Julian hello world.jl file. Okay, that's mostly about this very first hello world example, and we can get it done. Okay, I can share the link to the, I'm sorry, let me share this link. It's to copy, and I can share. Here we go. I'm just pasted the link to the slides, and this slide has been used for a couple of years. I'm keep updating the same slide, so it's like a live document, and if you see some differences in the future, then that's expected. Sorry about it. Okay, so far so good. So we copied it, we get it since running. So now just think about it, step back and see what we did. So first we log in the system. It's a system running on a big computing center room somewhere. Here on our campus, it's on the West Campus Data Center. And then we created, we went to the scratch space, and we downloaded the files and unzip the file. We go there, we load the module. Here, I didn't show the module loading here because it's on my previous slide. So supposedly, you already loaded your Julia environment. So after Julia is loaded, you can directly run this example. So technically, this is all set for advanced users who are new to the bigger machines, but they are familiar with Julia programming. So they can copy and upload their Julia program and follow the instruction here and run their code directly. Okay, so that's not all about it. There's one more thing I didn't mention here. Okay, this is already done. I believe this installation is done. Let's Control D. CD scratch Julia example. So there is one more thing. When you're on the computing system like this, you're not supposed to be using the front end all the time. Sometimes you want to run big jobs, like I'm trying to show here. So this is a small job, but if you want to run a big job, you cannot run on front end. You definitely want to run on the back end, on the computing nodes. So how to do it? You create a script called a job script, and you can submit your job through your queuing system. So there are multiple queuing systems. The one currently running and we are supporting on our system, it's called a Slurm. And you can take a quick look at the Slurm, SLURM. And the command line to run is, I already have this example. So if you get it on TARD, you are currently in this directory. What you can do is simply as batch and this job, Julia job sh. So what it does, it will submit a job to our queuing system. SQ. So this shows you all the jobs you submitted. So currently we do. So at the bottom, this is the jobs I just submitted to CPU. I didn't specify GPU node, but we don't need it for this tutorial. But in the future, if you want to run a GPU or want to run it on CUDA, it's fine. I noticed there's another user here just submitted another one here. It's great. So we can see someone's submitting jobs running on our machines. That's a starting point. So we're all done with all the job submission and running on big machines because the next thing will be your job. You need to develop some of the best programmers using Julia and just run it on big machines. And we are all set. And all you need to do is just modify this job script. And oh, I'm sorry, I accidentally submitted another one. I just want to show you all what's this script. So modify this script to make sure it's meeting your requirements. For example, if your job is expected to run 10 hours, currently this one is only 10 minutes. Make it very short, very small, make it easy to run. The system will squeeze it into the queue, make it easy. You don't need to wait for a long time to wait for the long allocation, big allocation. A small job, we are just requesting one task and 2 gig, about 2.5 gig memory. That's relatively small nowadays. And then you need to specify your account number, which one you want to use if you have multiple ones. If you don't have multiple ones, you'll use your default account. So you can also specify the email and also other information so that whenever your job is done, you'll get an email about notification. So by modifying this job script, you can reconfigure our system. Remember faster, right? You can request 200 tasks, and then you can request probably 10 GPUs, depending on how you do it, but the system will come up with a virtual system for you. You can run it on our faster machine. Okay, let's get back to the slides. Do you have any questions so far about running the job script or running Julia on the big machine? If you don't submit a job, if you don't run as batch job script, you are running on the front node. The front node, we have a limited number of front node. Everyone is sharing. Some people are using that front node for compilation. Some are using the front node for debugging, for testing. You're not supposed to be running your jobs on front node. That's the general policy, right? Unless it's just for very quick, small run, it's fine. But for big runs, you're definitely asked to submit your job through our queuing system. Okay. Again, all what I did before, previously applied it to not just Julian, many other just similar job script and similar way to set things up. It's just for Julian, we just need to make sure we load all the Julian environment, and that's all. Okay, that's great. So let's let's get started with the Julian. That's the main topic. So after you get started with Julian, you can start running things. That's great. So a quick start. After you get to the Julian prop, I assume everyone has this Julian running now on your computer, and you can try typing while I'm showing this and going through all the slides. Feel free to typing. It's how you practice, how you learn, right? So the very first command you want to try out for Python Julian is the first thing I always try: TensorFlow and PyTorch, just version information and version. And this will print out the version for you for Julian. And you can see which version you're using. This is very important because for some software you're developing or you might be using, they have a dependency on some old version of Julian. If sometimes you spend like a day to debug the problem, but it turns out actually you're using a newer version of Julian, then that your code might not be working well with. So that will save you some time of debugging if you're using third-party code you're not familiar with. Even your old code, after a couple of major versions or a couple of minor versions upgrading, some of the functionalities might not be available anymore, and you want to replace with some new functions and even new interfaces. Also, Julian has a very nice feature of providing this, how to call the encryption, not just simply based on ASCII data set. It's using the, how to call it, I'm not sure. It's it's a new encoding table for running all this. Never mind. I'll come up with that. But it's just like instead of using ASCII code, you can use emoji and some other symbols that you're using for typing stuff on your papers or on your work documents. One example I can show you quickly is the what's this? Let me go back to the Julian. Let me run my Julian here. So you can do backslash and tab. Oh, I'm sorry, it's SQRT tab 7. I'm sorry, it seems it's not working. Okay, it seems it's not printing out properly on this prompt, but let me try something else. Probably the one I might be showing you. Good. No, it's not showing on this, so it's that's probably one of the issues with I'm sorry, with the web-based shell. But never mind. I'll get back to y'all with a different solution. Probably if you want to log in with your terminal, this will be working out perfectly fine. And I do have. Let me see if I can get this one work. Master HPRC. So currently I'm logging through my terminal. This is on my Mac. So this on my Mac, but it's after it's connected to the terminal remotely, it's actually running the terminal remotely on faster. So the example I just trying to show you all, it's this one. It's not working on the web-based terminal. I'm sorry, it's actually not just this one. Many other things might not be working nicely on the web-based terminal, but this terminal is just regular terminal works fine. And just want to let you all know that it might not be working nicely with WebEx terminal. That's it. So the beauty about this, all this symbol is that you can use all the mathematical symbols you're familiar with, and directly using those symbols as your variables. Again, Python also supports this, but it's just working in a different way. And Julian has this built-in support, which makes it very, oh, it's great. Thank you so much, Wesley. So for those of you probably can see it, it's great. You can get this on the web-based term, but on my case, for some reason, in my case, for some reason, it's not working properly. So there are some key bindings you want to get yourself familiar with. And I cannot show you each one by this, but the most commonly used one is exit. If you get into the so-called REPL terminal, which is a command line terminal that I just showed you all, Control D is the one you want to use to exit. It's kind of like a Python. So in many ways, Julia is very similar to Python. Some people call it Python ++, and it makes sense, to me, because there are so many similarities between Julia and Python. And then you can use a Control C to interrupt, which is a pretty standard way to do to cancel and interrupt. And also you can clean up the console screen with this Control L. And there are some others, and you can try them. So let's get to, I noticed there's someone. Which is a calculation. Yes, I think sometimes I have different ratios, aspect ratios. It will not work with all the loading or the prompt, but it's fine. It's not essential for running Julia code anyway. It's just like the web-based interface might not be working properly. You can always try out on your terminals and some other editors, and Julia is supporting. So the very first question you want to ask when you start with Julia, why? Why do I need to learn a new language, and what it is, right? That's the very first thing I ask myself when I start looking into Julia. And Julia is a high-level general purpose dynamic programming language. So it's a lot of words here. High level means it's not like as assembly language or or punching cards. That's when you compare about the programming language like 50, 60, even 70 years ago. And it's born in MIT's Computer Science and Artificial Intelligence Lab in 2009. So it's a relatively new compared to Fortran, which is, I think, 50s, 60s, 1950s, 60s. And that's, this one is brand new. It's like a song of a Fortran. And it's working beautifully. And it combines the best features of, Ruby and MATLAB, C, Python, R, and many others. And it's first released in 2012, so after 3 years of development at the lab. And the latest release, as for now, I checked just several days ago, it's 1.8.5. If you download direct from the Julia website, this is the version you have. So for those of you who are not familiar with the version, numbers, we have 3 numbers here, like version 1.8.5, right? So 1 here is called a major version, and 8 here is called a minor version. And 5 here is called patches or bug fixes. So if you have major version, if you jump from major version from 0 to 1, that means you have some major upgrading of your code. It doesn't need to be Julia, many other, even for Linux. If you go from, say, 0 to 1, that means there will be major changes and there will be some features not backward compatible. So if I rely on code on Julia based on 0 point something, it's likely some of the function won't be working, very likely, and it's almost guaranteed. Otherwise, I won't bump it to a new version, major version. 8 here, it's called a minor version. Minor version usually give you some volume messages if you have some features got deprecated, and they want to throw away those, replace it with new interfaces. So bump to a new minor version, but they'll give you some volume messages. The final one, 5, it's almost, you don't worry about the last one, mainly because it's mostly about bug fixes. There won't be any changes in the features interfaces. Okay, for those of you who are familiar with this, it might be trivial, but for new users for open source software, you should keep in your mind, if you're using some major versions, you don't want to easily jump to a new major version, mainly because a lot of things won't be working. And it's customized, highly customized for greedy, unreasonable, demanding programmers. If you're a brand new, programmer and you want to learn programming languages, Julia it's a good starting one, but I would highly recommend Python as a starting language. Julia is good, but there are some tricky things and in Julian, and it's kind of hard for you to grasp at the very beginning if you are new, brand new, to programming languages. But if you're already familiar with C, Java, or Python as languages, learning Julia is just like how can we say, moving from Texas to New York, right? They have different accents, but it's easy to communicate. For me, I can naively just type in something I expect Julia to work, and it usually work, unless there are some different functions imported by different libraries. I don't know the names of those functions. That's the point I'll get stuck myself. But in most cases, it just works perfectly, and all the basic functionalities are very, very similar to some other languages. So that's the beauty about Julia. It's just like trying to use the common knowledge about programming. Meanwhile, it's trying to improve the performance underneath, and it's a pretty decent way of doing this kind of have this kind of project. So Julia Computing is a company established in 2015, and they are providing commercial support. So as you know, there is a JuliaCon I believe now every year. You can go there, and a lot of developers and researchers are using Julia for their research work. And also there have been a lot of applications in industry as well, especially in machine learning, scientific computing community. So this is an example showing you the performance of different languages. This is a kind of like an older one. They're showing this on Julia website, but take this with some thought. It might not be the real performance you see, but it gives you some comparison. It's better than nothing. So it's starting with the C language as a reference point, which is very standard because C is supposed to be the closest to the lower programming language, assembly language. C can control memory, can control pointers, and do a lot of lower operations on the computer. So C is usually used as a reference. So as you can see, Julia is doing pretty well. And actually, in some cases, it can go faster than C. And some of this, you might ask, how can it even be possible? One of the reasons is it's probably for very special, algorithms. There are different cache reuses and also other tricky optimization strategies that Julia can do that C might not be able to do it. So that's how Julia can, outperform C in certain benchmarks. But it doesn't mean that, it's definitely faster. But as you can see, many other benchmarks, it's actually cannot beat C. Again, for some other packages, you can see there are some other, especially this green one, this use functions Mandelbrot. That's the one I'm going to show you the example. This one is usually faster in a couple of languages actually than C because they have been doing some optimization, in a way that usable for the particular application in those languages that make it faster than C. But for many others, you can see, and Julia is doing pretty well as far as the performance is concerned. You can find this plot on Julia website. It's their official announcement. So another perspective, what is on the vertical axis? So the vertical axis, it's the popular, I'm sorry, this is the previous one. So I'm sorry, for some reason, here we go. So vertical axis, it's like a ratio compared to the same benchmark running using the C language on the same machine. That's what they did. So it's like a ratio comparison, how fast it is, how as a speed up. I'm sorry, that's probably the right way to say it. Basically, it's just a speed up on the y-axis. As you can see, Octave, which is open source version of MATLAB, it's really slow in some benchmarks, but let's give you some idea about how fast Julia is. It's pretty fast. So this is another programming language ranking that I have been following this for many, many years. I have been learning programming 20 years ago, started with the Fortran myself. We had a course, undergraduate course to teach Fortran. So I took Fortran 77 and later learned Fortran 90 myself, and then start doing some web programming using PHP. And also I had to learn Perl a little bit for a short period of time, and then start learning CUDA, also C and C++. So those are must. You have to learn C, which is it's a foundation for many other programming languages. And some of you use those old programmers. I'm sorry for using the word old here. Probably familiar with the Pascal, which is used for teaching algorithms in many computer science curriculums. And also have R, and at the very top here you have a JavaScript and Python. These are like a popularity based on the ranking on GitHub and also on the questions you ask on Stack Overflow. So Julia is not. It's ranked actually pretty high, based on compared to many other languages, because it's brand new and it's getting really popular, and it's a lot of young generation programmers that like it pretty much. And there are not many, but there's not a lot, but there are several startups just based on Julian. So there have been a big trend in the startup community, I would say technical startup community, using Julia for their projects, which make it pretty popular on the internet. Okay, with all that said, so Julia, the basic features, major features are fast, as it's a very general purpose programming language. Consider it's like a Python with a steroid. Basically, it's fast. You can easily leverage all the computing resources on your machines, and it's very pretty technical in a sense. A lot of new features and new algorithms and new ideas in the computer science community have been adopted in the Julia program language development, because the guy who behind Julia is a very, very famous computer scientist, and they have been using all the knowledge they have to make this Julia a real fast and decent programming language for mostly scientific computing. And a very big application of Julia nowadays is so-called scientific machine learning. And they got a lot of funding from Department of Energy, supporting different projects and DoD, and also they are supporting some of their ongoing research and project carried out by the Julia team. So again, this is probably you can consider this like a future direction for a lot of scientific machine learning. Consider it's like upgraded version of Fortran plus Python, and give you the benefits in both words. Sorry. To get you started, you probably want to start with some IDEs. IDEs, so-called integrated development environment. For those of you who are new to programming languages, IDEs are designed to facilitate the development of projects, software projects. It helps you to do the highlighting, help you to easily find the help information, help you do the debugging and compilation, and everything, profiling. If you're not familiar, especially for optimization of your code, a lot of things can be provided by IDEs. Some famous IDEs you're probably not familiar with. Some of them are using Python. You're probably familiar with PyCharm, Spider. What else? You can use Eclipse, which is a very famous platform developed by IBM, and then they're now supported by Eclipse Foundation. Those are very good IDEs for different program languages. And Julia has Juno, which is a very powerful way for you to do the visualization and other things, debugging even for running the Julia code. And another very famous interface for Julian is wait a second. Let me check the question here. It's a speed up. Yes, it's just a ratio. And okay, yes. Thank you, Marinus. So Jupyter, for those of you who are familiar with Jupyter, Jupyter is the first JU here is a Julia, right? Julia, Python, and R. So it's basically it's an interface designed to support Julia, Python, and R. So technically you are supposed to be running Julia just like you are running Python on Jupyter Notebook, but you need to make sure that your Jupyter Notebook interface recognizes your Julia backend. Otherwise, it won't be able to run anything nicely. Most of you install Jupyter Notebook through Python pip install Jupyter Notebook or Jupyter Lab. And by doing that, it doesn't recognize your Julia environment unless you have some system environment already telling this installation that your Julia installation is there, and so that it can find it. But you can install Jupyter Notebook through Julia interface that will make it work for you nicely with Julia. I'm sorry. So it's a big plus for Python developers. If you're already familiar with Jupyter, everything else is just like the same way. It's just the language itself will be different. You'll be using Julia, program instead of Python, and everything else will be identical. So there is a so-called repo here. It's, the command line interface I have been trying to show you all the time. This is the one usually people use on web-based shells or terminals. So repo here stands for read, evaluate, print, loop. So that's REPL, or repo. Some people call it repo. So it's a command line interface. So those of you who are familiar with Python, it's kind of similar. You have a similar command line interface. And repo is built into the Julia executable. So it's has this web-based, not web-based. This command line interface for you to interact with a Julian executable, and so you can do interactive programming. Exactly the same way we are using Python, using the Python prompt or IPython prompt, something very, very similar. Okay, there's not too much about this one, but there are some shortcuts, and something I mentioned. You can use a question mark just for help, which will be very useful. And I use that a lot myself, even though I've been using this for a while. But once in a while, you'll forget something, and you can use a question mark to get help from it. Okay, so that's the first two parts. Hopefully, you all have some rough idea about what Julian is and what Julian can do. And then we'll get started with the real meat, and we'll get started using Julian as a calculator. And all the languages could be used, almost all. And there are some languages might not be designed to do this, but almost all the languages have this calculation capabilities, right? So to get started, you need to know that for doing the calculation, I'm talking about just using a calculator. You input some words. I'm not talking about using this as an advanced calculator, like the one I'm showing here. You can write programs about it. That's something to the next level. But I'm just thinking about doing the very simple number crunching kind of calculation. So you need to be familiar with all the arithmetic operators. That's something we learned from elementary school: plus, minus, multiply, divide. And here there's an inverse division, which is something I'll talk about that in a second. It's a division, but it's just the way how the division is done. And then you have a modular. You can get a mod, and then you can get the power of something, a to the power of 10, etc. So these are all the standard ones. And also the orders are exactly the same, like we learned, because that's already a de facto standard. I'm not sure there's an international standard for how you do all these arithmetic operations, but it's a de facto standard. That's something we learned from elementary school. So nothing more, nothing less. It's just the same way. If you're not so comfortable with the way how the operation is done, you can use the parentheses all the time. Just ramp up everything with the parentheses. Everything inside the parentheses will be guaranteed to be evaluated before the result of whatever inside the parentheses got used for something else. So these are some simple examples. When I was teaching this in-person tutorials and short courses, I just stay here and just, hey, guys, just type in all this, just get yourself familiar with, get some memory, get some muscle memory, on your fingers, so you can get familiar with all the prompt, but it's fine. So one thing you want to try, if you have a terminal-based, I just want to show off something here. Say I want to do pi. It's automatically loaded, so it's already loaded. So you can use the pi. Use the up and down key. You can go back to your previous, command, etc. So I use a pi. I can times Euler number. So this will be, I'm not sure, Euler. I think EULER. So it will give you the Euler number, and with this symbol, and it's a mathematical kind of math type symbol, and give you a very nice structure. You can get this calculated, and just like pi times E Euler number. And you can have multiple statements together with a semicolon separate them. You can use a plus equal sign. Basically, x plus equal 3.1. Basically, it's just like you can do x equals 1, x plus equal 1. You'll simply add 1 to the value of x and set the value of x to x plus 1. It's equivalent to x plus 1. It's equivalent to this symbol. Okay, now to this statement. Now you can do you can play with arrays, and also there is a dot operation. I'll talk about that in a second. What it does is do the, I'm talking about the last line here on this screen. So I can start by setting my x to be an array of 1 and 2, just two numbers, just 1D array with two numbers, two elements. And then I do a dot power. What it does is just applies whatever behind this dot symbol to every element. So that makes it very, very easy. So you don't need to write a loop anymore. For those of you who are familiar with other languages, you always have a looping, right? You have a for loop, while loop. You can loop every element in your array. You can do something. But here with the dot operation here, you can directly apply this element-wise operation directly with a dot operation. So this is one simple example. Let me zoom in. So x equals to 1, 2, 1, 2. So give you a create a two-element vector for you. By default, it's an integer. Not default, actually, because I don't put a dot. As you can see, if you put a dot, put an extra dot, it will recognize this as a floating symbol with 64 bits. That's 8 bytes to save my data. That's a 6-bit system. If you have a 32-bit system, it will save at 32. But most of machine nowadays is 64. So you don't need to worry about it. Everything's working as expected. Now, the next thing I want to show you all is this minus 2. So what it does is trying to apply this inverse square of x. Is x to the minus 2 is actually equal to 1 over x squared, right? So when you do the inverse, and you can see it's applied to every element. So you'll get 1 and then 1/4. So that's what is expected. Okay. So you can do the same thing on your prompt. You can see the difference. But these are something every program language can do. But here, the one particular thing I want to show you is the last line here, the dot operator, which is kind of unique here for Julia, and also this symbol. I'm asking what's it? Just give me a second. Let's see. Let's see. I'm sorry, it's Unicode. And I have been, that word has been in my mind for a while. It's Unicode. So basically, it's able to use Unicode to represent every symbol, and then it's able to give you a very, very nice mapping to mathematical equations you're writing in your paper. You can, in some cases, if you have a Unicode representation, you can even copy paste. There's some program help you to directly, convert your LaTeX into some code, which is very, very nice. So that's numbers, and then you have rational operators like a equals to b, a not equal to b, a less than b, greater than b, or less or equal to b. Those are similar, but again, you can use Unicode symbols like not equal to, and to show if a equals to b or a not equal to b. So I'll show you one example. So for example, I have okay, so what it does, it's using this operator as a function. It's calling this function. So this operator itself is wrapping the function. It's saying, does 4 or 5 equal to each other? If it's not, then it's false. If it's equal to, I'm sorry, if it's not equal to, let me try this one. If it's work, it's opposite. So this one is not working because it's not say this is not defined as an operator in the same way as like a not equal to symbol. So you should be careful. Don't overuse this functionality provided by Julia. But it's a good way to keep in your mind that it's made it possible. So 4 is less than 5, less or equal to 5, less or equal to 5. It's 2 because 5 could be equal to 5. So this kind of symbol can make it easier for you. You can also do this. It's equivalent, but I definitely prefer the first version, right? Like most of you who are more familiar with mathematical equations. Okay, so you can try all this yourself. It shouldn't be hard. It's the same way. I don't need to just elaborate every one, but you can do the logical A and B. So you have A equal to B, B equals C. What if both of them are needed to be valid at the same time? You can use a logic. It's the first, with the first statement and the second statement they're the same. If the same, then you'll return 2. Well, let me go back to this one. Say, and 4 is greater than 5. It returns a 4 because if the first one is true and the second statement is false, then you get back to false. So that's expected. Okay, let's. I'll skip this one. And also, there is a very interesting difference in the NaN and the infinite here. INF and the NaN, both of them are defined in so-called IEEE 754 standard. So NaN itself stands for not a number. Anything you generate in your code that is not a number, it will be marked as a LAN. And actually, if you're familiar with scientific computing using Fortran or C, NaN is something you have like mixed feelings. Sometimes you definitely, when you're running your code, don't want a NaN, but when you have any problems, you want to debug your code, you want to catch NaNs because those NaNs will be the place where where your algorithms or your code will be failing. So there have been a lot of effort to write NaN counters and those kind of things just for you to capture where the LAN first happens. Then you know which part of the code is wrong and it's really helpful for you to debug your code. So LAN is usually treated as as a very special, unique thing in this floating point definition, floating point standard. That's IEEE 745 standard. Infinite, it's something I'm not sure it's relatively new, but it's relatively new to me, at least for C and I believe C and Fortran. We don't usually use this. I'm not sure if C is currently supporting this latest version of latest standard of C or C++. Back then, you can either get NaN or number. So that's infinite is not supported in actually when I was working on those program the scientific computing code. But now with Julian, you can define NaN as it's a floating point. It's a part of the floating point definition. So it's an infinite. You have a positive infinite and negative infinite. So NaN and the infinite, they are different. So NaN and NaN, that could be equal, but when you compare NaN and infinite, they are different. So you can always compare with a negative number to negative infinite. So always, negative infinite will be the smallest number you can get, and infinite is the biggest number you can get. But NaN itself is just not a number. It's not any floating point or anything. So, yes. Look at the last statement here. 1 divided by 0. In Fortran, I'm not sure about latest version Fortran 95 or Fortran 2000, but back then Fortran 77, I believe Fortran 77, when I was working on that, it will definitely give you a NaN. And actually, you can consider it's an infinite, it's INF. So it's definitely not NaN. It's a number, but it's an infinite number. That's how you define, all this definition will help you in some comparisons. If you are working a lot on scientific computing programs, telling the difference between NaN and infinite sometimes will be helpful for you to debug your code. You might be getting a number, but not NaN. NaN will usually sometimes you get a memory problem. Some values got you want to rate a floating point, but the system give you a string or give you a character, and that's kind of problem when you're dealing with debugging your code. But again, this is something you want to pay some attention if you dealing with code development in real life. Like most languages, you need to define variables. Variables is so powerful, right? It gives you the power to deal with generic cases. You don't need to deal with the numbers 1 by 1, so 1 or 2. Give you a number. This number could be representing the whole, real world, real numbers, and that's really powerful way of thinking, right? So, defining a variable, you're more or less like allocating the memory inside your computer, and the memory will holding this variable, and this variable could be changing, could be any number. And you can start doing evolutions. You can do a lot of things with that. So that's a starting point of a real programming. If you're just dealing with the numbers, 1 and 2, 3, you are doing calculation. With variables, you can define functions and you can write programs can help you to do all the work without you specifying all the numbers specifically. So it's giving you the power to do the automation. Okay, so all these are just different functionalities that Julia is providing for you to define a variable, and you can get a type of it, like a type B here will give you a type of variable. Here is say Boolean. Now let me just do it quickly. 2, and then you can do type of. You can use auto-completing with a temp key. You can give you a Boolean, which is only true or false, right? And also you can let's see. You can use a variable info. Not sure, I don't use this much. It will print out all the variables currently defined. So as you can see, I defined a B and X previously, and you can see it's like a variable table using MATLAB. If you're familiar with MATLAB, so it stores this. I believe Python also have these functionalities now. It stores all the variables you define, so then you can go back and check whatever variable in your memory, and it's really helpful. So you can do other things. You can use also Unicode to define variables. You can make your code really fun to read, right? You can define a football equal to 2, and you can define a runner equals 1. Then you can, let me see if I can football equals to 2, 3. Let's do football to the power of 100. Okay, see, it's pretty neat, right? So that's why I believe there have been the Julian computing has been trying harder to teach kids to use Julian, and they have been developing some modules and tutorials just to get kids started and make it pretty fun to use this Unicode, and they can do a lot of fancy stuff with emojis and other things. So, like many programming languages, you needed to be careful about naming rules for variables. You cannot use numbers to get started. If you use a number, say 4c, equals to 12, it will give you an error, say 4 is not a valid function, arguments, whatever. So it's treating this 4, it's when it's parsing this prop, because it's starting with a number, it's not treating it as a function name or a module, a variable name. Otherwise, there should be a problem. If you use a C4 equals to 23, everything's fine. C4, or you can use a underscore. It's also fine. So it's just like tradition. I don't think it's with what they currently have. There might be some ways to go around this. You can get started, but it's just tradition. No one wants to use 4 these numbers as a starting character for the name. And also there is some. It could be a tradition. Another reason could be there's some ambiguity in when you're parsing this string. 4c could be passed as a 4 times c. Depending on how they want to expand their way of defining all the mathematical expressions, and so just as far as this short course is concerned, just follow the rules, and everything will be working fine for you. And there's no way to fight against this. If you, it's not like a civil case. You can just go to a court and claim, right? But just follow the instructions. So the maximum length of variable actually is not limited. I never tried how many times. You can, some of you might be crazy. You can just try, crazy long name. But oh, I'm sorry, I got multiple. You cannot have a space in between. You can have non-name. And in some languages they have a limitation, but in Julian it's I believe there must be a limitation here. I just need to double check. I don't know there was a preset limit for number of lengths of variables you can say. The variable name A is different from capital code case A, so it's a case sensitive. So it's the same for many languages. Fortran is kind of different. I know BASIC is also case insensitive. MATLAB is case insensitive, and many others I know there are case sensitive, case sensitive. So this to display a variable, it's simple. You can simply print it out, or you can just type it here, just like when trying to do x. I already defined x. I can just type x, or I can do print x. I'm sorry. So there's print isn't. What's probably space. I'm sorry. I get too used to the free format here. You cannot have the space in between, otherwise get confused. But anyway, so print x will print out this, and then you can have print x with new line. So what it does is print x and print a new line. And I don't think it's really that helpful, but it's at least it's some, just in case you want to get a new line and give you some prompt. Okay, so a very simple exercise. Now I have a equals to 4, b equals to 17.2, and try to type on your prompt to do all the calculation. I'll give you probably 2 minutes, and just try it out to see if you can get anything out. So here we are doing two things. First, we define two variables, a and b. That's good. A and b could be any numbers. And 4 and 17.2, this is just arbitrary number. And below, we are already working on some mathematical expressions. These mathematical operations could be wrapped up in functions. By defining a function, you can do all the same calculations, just simply a function call. A function is a building block for something much, much bigger. And Julia itself, it's a functional programming language. It's treating functions like variables. So after we start talking about functions, you'll see how powerful it will be. But currently, we're just doing mathematical calculation based on the variable we have. Okay, I don't think we need that long, but I just tried it myself, typing on my computer next to me, and it seems it shouldn't take that long. So let's skip to the next one. And after we define all the variables, the next thing we think about is how can we use the variables to do something. In the same way, when you're learning a language, new language, you start by learning all the words, then you start building sentences, and then you start write multiple paragraphs, and then you build up you can write articles, you can write books. That's how you start building up your capacity as a writer, or as a language learner, right? Now, learning a new programming language is started by understanding of the basic syntax. If you're new, if you're already familiar with other programming languages, the syntax is almost trivial. You know all the basic words. It's kind of like, I'm not sure, I learned a little bit German when I was in college. And there are some similar words, and it's not like this, it's not like a Python and Junior, it's almost not identical, very, very similar. German and English words, there are some similarities. So for me to jump from English to German, it's relatively easy compared to jumping from Chinese to English. So with that said, it's kind of similar. If you already familiar with some programming language, and the barrier, it's actually very, very low for you to get started with Julia. Okay, so the basic syntax for statements. Now we start building sentences, not just define variables, right? We want to have paragraphs building up, and the sentences here is corresponding to the statements, and then we have multiple sentences together. We build up paragraphs. So what is a statement? Basic statement, we can start with this pound sign or sharp sign. I'm not sure which one is correct one. So you can use that as a comment. It's not like a Python. You can use that anywhere you want. So you can have I'm sorry, whatever you want. It's just the REPL. Do you know what a REPL is? Remember? That's a command line. That's what we're using here. We'll just take this comment as some comment and just ignore. It will not execute its evaluator because it's common. It started with this symbol. Or you can do x equals to 5 and comment x equals to 3. What it does, it will evaluate the first part and ignore the second part, because second part, everything behind is this pound sign or sharp sign. It's a pound sign. It's a comment. So it will just ignore that part and just evaluate the first part. Okay. It's Python comments is working the same way. It's useful, very useful for comments, because if you are writing any code, it's very, very good practice to put a comment in your code. After a short period of time, you'll forget about it, complete about what you're writing if you don't have any comments in there. Even though it might be easy for you to pick up quickly because you are the one wrote the code. But after a long period of time, it's even, a decent programmer, it's kind of hard to recognize his or her own, writing in any programming language. It's kind of hard. So putting in comments there will be helpful. So there are also some extra comments. In the same way, when you're writing comments in Python, you can use some external software to help you, like a Sphinx, generate the documentation for your Python code. Julian has a similar, documentation software that you can use, and that's where we'll be relying on different structures. For example, you have a triple quotes, and you can definitely will use that as a comments for the whole program, and you can insert some other comments like markdown strings, and it will generate all the comments together the code, give you a very nice documentation about what your input could be, what your interface should be, etc. So that's a little bit beyond our short course today, but just let you know, these comments are really, really powerful and useful too for you to keep record yourself and also help others get started with your code. Now, Julian has multiple ways to get started. You can define a begin and end. That's kind of like, I believe Pascal is using begin and end. I don't remember other languages using begin and end as a starting, as the quotation for your code blocks. You can use a parenthesis. It's all, many languages using parentheses. Python you can use a parenthesis to wrap everything up in, and C is using curved parentheses, and it's in a similar way. So by doing that, you're defining this Z as the you're getting the output of this whole statement, and set that into Z. So what this Z is? Z basically is a text, whatever your output will be from this statement. So we can try this out ourselves. Let's see, let's go to the prompt. We can set Z equals to X equals to 1. Okay, and X plus 4, X equals X plus. No, I'm just writing this randomly on myself, and it's X plus Y. Now, what it does, first is evaluate X equal to 1, and then you plus 4 to this 1, X, so you get 5, and 5 plus 1, Y is not defined, so it's, probably it's better to get Y, I'm sorry. So then this Y will be defined. So X plus Y will be 5. So my Z, if you put it, it would be 5. Now, that's the tricky part. What if I do this? If I say if X equal to Y, so the value of Z will be saved as a final output from this whole statement. This actually it's a combination of 3 statements already, even though it looks like one simple line, it's already 3 statements. So what Z is taking, it's taking the output from the last statement, and whatever output from that statement will be saved as a value of Z. Okay. You don't usually use this a lot, but just in case you notice some people writing code in this way, it's good to know that you can define your blocks with the beginning and end, and also parentheses. I prefer the later one. I don't say I'll use the beginning and end myself in my coding, but it's good to know that it's supported. Oh, of course, if you use a begin and end, you can use multiple lines. You don't need to type the semicolon. But if you're putting everything in one line, you can use semicolon. And at the same, I think it's a basic syntax is similar. So I'll go through this quickly. Okay, so we talk about variables. We learn how to define statements, and then we'll get a bit deeper into all the numerical data types supported by Julian. And you can see here, this shows very high level overview about all the numbers supported by Julian. We have real numbers, as long as you can write it, you can find it. Given a real number, you can always find where it is on the number line. That's what I call the real number. You have a number line from all the way from negative infinity to positive infinity. Real number are the numbers you can find on the number line. And a complex number is a number you can find in the complex plane with X and Y, which is an imaginary and the real. You can always find a point on this like a 2D plane, right? You can find a point, and that's your complex number. And then complex number is simply a combination of 2 real numbers. So you don't need to expand further the complex number branch. So look at the real numbers. You can have abstract float, which could be float with different length of the representative could be 16 for 16 bit float. Basically, that's you use 16 bit, like 2 bytes, to representing the floating point numbers. That's called a I believe this double precision is 64, single precision and it's 32. The 64, that's a half precision. That's a 16, that's 2 bytes. Then you have a big float, which will be you can have I believe there is a preset environment variable that you can determine how many bits you want to use to store your floating point, so that you can have extremely high precision depending on what you need. So it's storing your data in a different format. It's not following directly the standard, but it's just trying to keep track of all the decimals you can get, and up to the number of bits can hold. So for integers, you can do something similar. You have big integers, you have signed, unsigned, etc. And you also have a rational here, which kind of different. So rational is like a fractal, not fractal, fraction. 1 divided by 3. If you do it in Python, or I'm not sure if Python is supporting rational, I need to get back and check. But see, if you do the 1 divided by 3, it will store it as a 0.33333 all the way up to the I believe 16 decimal point, I believe, for double precision. And then you can, that's it. But in Jupyter, it support 1/3 and the 1/3. So that's kind of different from other systems. Irrational numbers, those are be stored as irrational, could be square root of 2, or it could be just numbers. But it's an irrational way of, that's a symbolic way of storing all those different numbers, which is a kind of different, make it easy for you to do some calculations if you are kind of concerned about accuracy. You don't need to store, pi to 1.34, you can store pi as pi, and then you can change the precision of pi by changing some system level variables. You can keep the precision of pi to that level. It could be 1.1415926, whatever, 58, all the way to the number of precisions you can keep. So signed, unsigned, those are only used for integers. For floating points, you usually keep the sign as a default, so you don't tell the difference between unsigned and signed. And there are also smallest number you can keep for the unsigned, but you don't put a negative symbol in front of the number that's unsigned. Usually it's always positive. So the smallest value you can get for unsigned integer is always 0. The largest one, as you can imagine, is 1 bit more. So you, instead of using the half of the the storage, 1 extra bit to tell you the symbol, you can use the extra bit to store more number. So you can get 8 bit, 2 times 8. That's how many? 4, 16, 255, right? That's 216. That's 8 bit. So you can go even higher, and then with more information, you can with more bits, you can store more data. That's basically what it is. So there are some tricky thing here. That's called a big integers. I mentioned about it. It's called a big integer type to handle big integers. You can handle extremely big integers. One thing you can do here, let me show you. For type max, for integer 64, I think it's integer, 64. So this is the maximum number you can set. This is a number, it's a numerical number. If you count, I don't know, how many you can even read it. It's how many trillion, billion, quadrillion, whatever. So this is a big number. That's a maximum number you can support with the current setting. But let's do this. By turning this into a big number, all you need to do is just put a big, which will convert this into a big integer, because this is an integer and you use a big, it will convert this big. If you do nothing, it's here. Okay, now if I want to do, say, this big number to this many powers, it will give me some weird output. It will be negative because it goes beyond the boundary of what's the maximum integer 64 can support. Okay, so what if I do this? I do say big, okay. So this is number I get. I'm sorry. I just want to just impress you all, and it's so many. You can try it yourself. Don't be crazy. Just give a small number. Probably more makes more sense. And actually, this can go extremely large numbers. So this is useful when you're doing, for example, we are doing say, find the largest prime numbers or etc. We're doing those kind of numerical number theory kind of calculations, or doing some encryption related, procedures. You might want to have extremely large integers to handle that, bigger than what this bigger than type max can support. Oh, I'm sorry. So when you're dealing with any number bigger than this, you probably want to use a bigger. So it gives you the power to handle extremely large numbers. It's almost unlimited, depending on sometimes depending on your memory and how big a number you can hold in your memory. Yeah, that's a good question. That's the problem I noticed. It actually didn't give me an error message. Just give me a weird negative number, which goes beyond and that do some like kind of like when you do the Python -1, it will give you the last element or your array, right? I believe it's doing some calculation based on it's like looping around the numbers they can support. But anyway, so that's you can probably change some settings to give you error, but I haven't looked into that myself. It could be a way to deal with it. So okay, let's take a short break, and then we'll get back at about let's get back number 310, and we'll finish the rest of the materials. And we already passed like 1.5 hours already. So, and for those of you who are just getting started on big machines, feel free to just try out, submit the jobs. Don't be afraid of breaking the system. Our system is pretty resilient, it's reliable, stable. As long as you're not doing anything crazy, you're not hammering our system, and it should be fine. Just try whatever you can. Just learn. Just test some limit. Try your thoughts on the code, and it's supposed to be a testing system anyway. So okay, let's get back to all the slides. I think we still have many slides to go through, but I think we have enough time today. So we have floating points, data types, and it's kind of similar. If you're familiar with the GPU computing, people talk about single floating point, half floating point, double precision, half precision, single precision. It's referring to 16 bits, 32 bits, and 64 bits individually, respectively. Half precision is usually used for machine learning and models, and greatly reduce memory and also computational requirements for model training and inference, and it's used a lot in machine learning field. But when we are doing scientific computing and scientific machine learning, double precision is usually the requirements, at least for many applications I'm familiar with. And handling floating point, it's a tricky. I have one example here that I've been using this for all my short courses on programming languages, and this is a very simple course. If you look at it directly, just doing the math in your head, your mind, A is 4 over 3, and B is, as you can see, if we subtract 1 from A, you get B is 1/3. Okay. Now C is 3 times 1/3. That should be 1. And finally, E is what? It's 1 minus C. It should be 0. Now, what will you get this in Julian? So let's do this. So you have A equals to 4 divided by 3. Okay, that's good. And B is what? A minus 1. Now you see something. It's not just, at the end of this floating point, it's not a 3, 3 anymore, it's a 3, 2, 6. Okay, that's called a truncation error. That's something you have to deal with when you're dealing with computers. Okay, now C equals to B times 3. Now, what do you see here? It's not 1. And E is equals to, say, 1 minus C or C minus 1, doesn't matter. So you get a number. Now you see it's a 10 to minus 16 number here. That's exactly the last digit for the accuracy you can achieve with a double, with I believe this type of thing. Let me double check, make sure I'm not telling something unfounded. It should be E. So it's a 64 bits, that's a double precision. So with a double precision, the maximum accuracy you can get is 10 to minus 16. That's already good enough for many applications. But if you're dealing with a highly dynamic nonlinear systems, a very, very small tiny difference will give you a dramatic different results. Like you probably see heard about the Lorentz system, or those butterfly. That's exactly the chaotic system. That's all the errors coming from, not errors. It's just like that's something you have to deal with. All these small truncation errors will be building up and something big. So it's just what we have to deal with, because we only have a limited number of digits to representing all the floating points, right? We are guaranteed to have some errors, truncation errors. So now let's deal with this with a big number, and you'll see the difference. The only thing I'll change will be just changing the very first number, because for all the following up calculations, it will be carrying the maximum precision it achieves. So here I get A equals to 64. A is equal to 4 divided by 3, and I do the same thing for B, same thing for C here. And then if you do the E here, it will be 10 to minus 1. Okay, and also we want to double check what E is. It's a big float. Now you see the dramatic difference, and with this, you can achieve extremely high precision. Quarter ball precision is nowadays pretty common in some, numerical simulations, and this is a way higher resolution than a quarter ball precision. But everything comes with a price. As you may imagine, this will be more expensive to compute. If you're talking about billions and billions operation of this big float operations, you're talking about a dramatic decrease of your performance, mainly because you have to handle this separately, differently. Oh, I'm sorry. Let's get back to the slides. Now, as I mentioned, there are some things you can do to change the precision. Now, with current default setting, your precision can give you, your current system, a big float can give you 10 to minus 77, okay? Let's try to do something even crazier. And let's try to set precision to, say, let's 4,000. I'm not sure, 4,000, doesn't matter, it's just any number. Let's do the same thing here. Okay, let's just do the first number so that you know what I'm talking about. So it'll give me extremely accurate number, and the error, as you can imagine, I'm not sure if we want to go through everything here, but we can do that. Oh no, we need to calculate C first, and then I do the E. So it's 10 to minus 1,204. So I'm just trying to, show you all with some of these dramatic numbers, and just to show, what Julia can do that traditional programming cannot easily do. Of course, it's supported by some other program languages, but Julia make everything is very, very easy to handle, and it might give you the freedom to pick the precision you want. And that's something really impressed me when I first switched to Julian, and really likes the way how they handle these things nicely on the programming side. So complex and rational numbers, it can be dealt with in a similar way. Nothing tricky, as long as you're familiar with how to deal with the complex numbers. Those are very intuitive. It's just working as it should be. And there's another rational number that I didn't show you all. It's using as a double backslash. It's a slash, not double backslash. It's a slash. H divided by 9, it give you this number. What if I do this? It will give you this fraction. before you evaluate this is exactly h divided by 9. It didn't do any calculation until you want to calculate it. If you want to do big this, it doesn't convert it because the fractal itself actually carries a higher accuracy, when you do the calculations. So this one, if you times 3, and you can see it's give you a fractal, a rational number, which is also highly accurate. If you time this to 9, now think about it. If you go back to our original problem, instead of doing this, let me do 4 fractal 3. Okay, now let me try to do b minus 1, and then try to do multiply, and try to do this. Okay, that's perfectly 0. So that's actually another power of Junior, but handle all this actual rational numbers and give you the set with element without running. So that's a hardware problem. That's a money issue. If you have money to buy enough memory to support that, it can definitely handle that. But again, as far as the number itself is concerned, it can handle extremely large number, but the size of the array depending on your memory. If you can, with that said, it's kind of different depending on how you handle your array. If you're doing this all the operations, element by element. If you don't want to load up all your element into your memory, you can do this, chunk by chunk or block by block, right? Then you can handle extremely large arrays as long as you have enough storage to store the data and load them, or depending on how you generate your data sets. And definitely the cluster, as long as I didn't do the numbers. Can someone do a quick calculation to see how big this one is? Consider this is a big array. Let's see how many. It's 1, 2, 3, 5. 5 points. Okay, it's 500 billion, right? It multiplies this by floating points, and that's 16. Let's say 8 bytes. That's a gig. That's a 4 tera. Can someone do the math? Help me. Probably 4 terabytes, right? We have each node. We have about 300 gigabytes. So if you request, I'm not sure about the current, but for grids, I know we have a 300 gigabytes memory for some nodes, and some even bigger, some even smaller. And if you do a cluster to handle this, I believe a 10 nodes cluster can probably handle your problem. Again, I'm talking just only one array. If you have multiple arrays like this size, you probably need more nodes. But again, if your array is going to be handled block by block, and you don't need to process all the elements all at once, a very small computer can probably handle that problem. It's just need to load up one by one and process them one by one. Does it make sense? So that's how you handle big data problem. You don't load all the data into memory. You load this piece by piece. If yeah, it's about 4 terabytes. That's good. It's handleable. It's even if you load everything up to the memory, our system, if you can request up to 10 nodes or probably 15 nodes, I don't know. Someone can also do the calculation. We can handle that in the memory, but again, in each node, you need to handle your elements separately. If you do a lot of communication, that will be a lot of communication cost. But yeah, I mean, feel free to reach out to our staff members. They can help you to figure out what we can do and can help you about the problem. And that's what we are doing anyway, right? So that's good. Thank you for the question. I'm sorry, getting back to the wrong. So that's the rational numbers, and there are some useful math functions. This will be applied to all different data types, all the numerical data types. They can all work perfectly. And there are some functions you might be familiar with, some functions you might not be familiar with, but they're all working nicely with the Julia. So I'll go quickly through this. And again, compare against the numerical types that most of us are familiar with. Some of us need to deal with the strings and deal with language processing. When you're dealing with now ChatGPT is getting really popular, and a lot of people are doing models, the build up models to parse articles and input data and then process. Those are most like a string processing and text processing. So you need to deal with strings in that way. But some way in Python, we deal with the strings and the characters, very nicely. The Python has many built-in features to handle that. The same goes to Julian. Julian has almost everything you can imagine with Python. You can deal with Python. You can do almost similar things. Almost everything you can do with Python with Julian. So the way that all the strings handled is almost identical to Python. You have, but instead of using minus sign, it's using end to representing the last character of your string or last character of your array in the same way. But everything else is very, very similar or almost identical to Python if you're familiar with it. So you can get a substring based on the index of your beginning character and ending character. You can get a substring from it. You can get an arbitrary number of characters from your string, and it's dealing with string as as array of characters. And each character is just individual character. As I mentioned, you can use Unicode, not just simply ASCII, with 255 characters in the ASCII table, right? You can deal with extremely large number of Unicode characters that, it's not a concern here, but we are mostly dealing with ASCII characters anyway in our real world cases. Sometimes you need to deal with Unicode, but not so often, unless you're dealing with packages dealing with different language sets, then you have to deal with a Unicode. And you can do so interpolation. I think this is probably the wrong way to say interpolation, but it's like interpolation. It's different from interpolation. You're talking about numerical interpolation, and it's trying to evaluate your evaluate a part of your string, and so then it will give you the expected output. For example, if you put a dollar sign here, it can evaluate everything inside is dollar parentheses, and in dollar and parentheses 1 plus 2 will be evaluated first, and then the results will be output as and converted into a string that could be show up. So a triple quoted string will be used literally. Basically, there's no escaping will be done. So everything triple quoted will be treated exactly like what it should be. It's just trying to avoid any other potential misuse of this dollar symbols, etc. And there are other examples. You can handle strings. You can do the quick search. You can do all kinds of things. As give you the location. Tell you if this particular string is inside this particular list of string inside this string. I'm sorry. All sense is trying to find out if there's a particular string is inside a string, and it gives you the location. And also you have a repeat. You can generate a repeated patterns and accept that, and it gives you the index, last index, and also the length of the string, etc. All these are very, very similar to what you can do with a Python. It's just like the functions are just different, and like the length here is just len in Python, and here you use length. And you can also use regular expressions. So regular expressions just like spells from a wizard, right? Some of you are familiar with it. I used it a lot many years ago, but after I stopped using it for a while, and I now don't remember a thing about it. It's just give you a quick way for you to match different patterns. You have a repeating patterns, you have space, you have any symbol ending, and to give you a very, very simplified and not simple, very, very succinct. I'm not sure it's the right word. Very, very a brief way to express your pattern, so that you can match the pattern, with a given string. So that's what this regular expression mostly about. Perl is really being famous for supporting those regular expressions, and now most of the generic programming languages are supporting general programming languages supporting regular expressions. In C and some other languages are supporting regular expressions using some libraries. But Python, I believe PHP and Julia now, and I'm not sure about JavaScript. For someone familiar with JavaScript can talk about it. But for the ones I just mentioned, they all support regular expressions with existing module like Python. Because there's a RE module you can use that to support regular expressions. Again, if you want to get help, online help, I'm sorry, like, you can directly use a question mark. It will give you to the help prompt, and then you can type in anything. It will give you, the help, and with some, with the example here, which is very, very nice. You can quickly search online documentation, but if you are working on a command line interface like this, it will be very helpful. If you want to go back, you can use let me see if you can use a delete or on Mac, or you can use a backspace. It will, just back. It will get back to your Julian prompt. The same way, when you're trying to use the right bracket for adding packages, you can use a delete on Mac or backspace on the PC. You can get back to the Julian prompt, which is very convenient for me to just look for any information, call sign, or for example, the one that we just talked about, big, maybe. Yeah, you can find all the information directly. So we already talked about, now let's try to briefly review what we did. We learned about variables, different types of variables. We have number types, string types. There are also Boolean types. It's very simple, true or false. So we didn't cover that. Mostly you're dealing with the strings and numbers in most of the Julian applications. And also we talk about statements. You can use Julian to build up statements, and then you can use statement to build up your programs too. If you have many statements put together, it's a program, and then you can run them. But now we are going to get in a bit deeper into Julian by talking about functions, which is a building block for Julia's fancy world of programming. And almost everything you want to write here, you want to wrap it up in a function. And the function could be easily shared with other people. It could be a very generic building block for something much, much bigger. And if you know how to build a function, it's like you learn how to create a brick. With that brick and many different bricks, you can build buildings, in different shapes, different style. Right? It's a similar idea here. So to the right here, I'm showing one example, and I'll get back to this one later on, but it's an example showing you how to plot this Mandelbrot, fractal, and we can learn a bit more about it later on. So what is a function? So function is like a mapping from one set to another set. It's mathematically. There are multiple ways to define function. It could be a full mapping, could be how to call it, inject, object, whatever. There are different ways of doing the mapping. If you have 3 elements in your function, in your X set, and you want to map 5 elements in your Y set, it's possible that you can have multiple values for each one. That's not a well-defined mathematical function, but in the programming world, your input could be anything, your output could be anything. Your function is trying to define some action items for you to act upon your input to produce the output. The output could be anything, and our input could be anything. So it's a pretty generic way of function. But in mathematics, you can always consider this as a mapping from an input to output, even though this might not be mathematically rigorous and might be completely wrong if you want to define a very well-defined function. But it's kind of idea that you want to keep in your mind. It's just trying to give you some output based on the rules you define in the function. So here I want to define a function to give me the summation of x and y. And this function could be, I define that function as a function f(u)(k), this name as my function, or I can define my function as a symbol here, the sigma symbol. I can define that as my function. So there are multiple ways to define a function as an operator, or you can define it as a function, a function thing. It started with a function ending with n. So whatever between, it's a function you're defining. Or you can define it just directly as a expression in the second way I'm showing here. So the plus function itself, the plus symbol operator, is an operator itself. It's also a function. As I mentioned to you, the not equal symbol, right? I'm using this not equal symbol as a function. Actually, it's defined. I can only use it because it's defined. I cannot use, I'm not sure if I can use this 3 and 4. Yeah, I can use it. So now I'm using this minus sign as a function. This function takes the 3 and 4 as the input. It gives me the result by acting upon 3 and 4 and give me 3 minus 4, which is minus 1. So that's what this minus function is about. The same goes for plus function. It's just working nicely that way. Okay. Also, you can define your a function to representing the symbol function. We can talk about it later on, but there is one particular thing that you want to be careful. So if you want to modify the arguments of the previously defined function, you need to append this explanation symbol to the names of the function that you want to modify that. Otherwise, it will be just taking exactly the same arguments as the previous function. So we'll have some examples later on, and you can see some of the difference there. So again, function is so important. And if you want to write a script, you can always start by just running all your line by line script on your Julia. It's same for Python, and get it run and check things out. But if you want to reuse the block of code you have been written, it's the best way to do it is just run everything up as a function. And then it helps for you to understand what your input should be for your whole block of code you have written, and also help you to identify the output you should return to the whoever want to use it in the future. And then you can reuse the same block of code by simply calling the function. So that's the way how you automate stuff and make accumulate all these knowledges and accumulate your experience into functions. So next time you just need to call the function, don't need to worry about what it's about. It's in the same way when you calling something to do the cosine sine, you're just using some other people's work. They already figured out how to do that efficiently. All you did is just call the cosine function. Think about it, you implement every single line of cosine function from scratch. You can do it, but might not be so efficient, right? You can probably spend days and months just to optimize it. But why do we need to do it if it's already there working and we don't need to worry about it, right? We just need to focus on the things that are really interesting and try to leverage all the functionalities the programming language can provide. So that's the whole purpose of doing all the programming. So you can, just like Python, you can define optional arguments. It's called keywords arguments in Python, or there are other definitions for that. But there are positional arguments, there are keywords arguments, or optional arguments. For the function here, point function, x and y, those are sort of positional arguments. So you have to have x and y in the right position so that this function point, when you call it, it knows the first argument you provide, it's supposed to be x. The second argument is supposed to be y. And then there is an optional one. This optional one needed to be, I'm not sure if it have to be, I mean, in Python, there are some particular locations you have to put this optional arguments after your positional arguments, so that Python knows that whatever you provide in the rest will be optional arguments, and you should tell me what this argument is about. And that's, since it's optional, right? So you needed to have some way to provide information to the function, for the function knows how to deal with it. So here, the optional argument is provided to the function definition with a default value. Without default value, the function, the Julia function will consider your input as a position argument. So that means you have to provide your z value. Otherwise, it's an error message. You'll get error message. So we can easily try things out ourselves. We can define, function, say, play. Let's do x and y and z, right? Oh no, actually there's no. I'm just so used to that. It's a function point, and then just print Again, you don't need to worry about the indentation anymore. And it's not like a Python. You have to get an indent properly, X and Y. If we do this, I believe it's end. Okay, I can define this. It's no problem. Even though, wait a second, I have to use. Let me try to play 1, 2. Okay, so if I do that, when I try to call my play function with only 2 arguments, it consider, hey, Jen, you missed one thing. I am looking for 3, but you give me 2. So you're not following the contract, right? That's more or less like the definition of the interface. It's like contract. You need to follow that contract. You sign it. You sign is just joking. You need to follow that contract, so then the function will execute your order. Otherwise, it's just telling you, say, hey, Jen, you're not following my interface, and I won't give you anything. So what I did, I add an extra argument 4 here, so it'll give me what I expect. Now, if you define this function in a different way, like say here 0 equals to say 4, I print out X and Y. It's the same function. It's just like I have, I'll tell a bit more about what it says. If you see at the bottom here, it says play generic function with 2 methods. So what I'm trying to say is play is a generic method. You can use play to in 2 different ways. That's why it says with 2 different methods. It's trying to define a generic function, but this function has 2 methods. One method only taking 2 arguments. Oh, I'm sorry, 3 arguments, because we have X, Y, Z as a positional arguments in my previous definition. Now I redefine this play, and I added another way to call this play function. For those of you who are familiar with this, let me just simply play 1, 2, and 1, 2 and 3. So it's just print out X and Y in 2 and 3. And now it's kind of like a polymorphism. If you're familiar with object-oriented programming, you have the same interface, but now you have different ways to call the function, and it gives you different ways to use it as polymorphism. It's the same interface, different arguments. And I'm not sure if we have something to cover about that, but if you're familiar with object-oriented programming, that could be later to you. But if you're new to this, it might take you some time to sort things out. It took me a while just to figure out why it's working this way. But if you can take it intuitively, consider it's working, then it's good. Later on, when you're trying to learn a bit more about object-oriented programming, you'll learn a bit more about this polymorphism mechanism supported by Julian, Python, C++, Java, all those kind of programming languages. It's non-trivial. It's not something coming directly for programming languages. C and Fortran that don't do this, and you have to write a separate function with different names. Otherwise, there will be a name conflicts when you're trying to call the same function name. Like here, you are calling this point function with a 1, 2, and a 1, 2, 3. They both work, and which is quite nice because you can deal with different input, but the same function will work. So keywords and the positional, that's something I just mentioned about. For the keywords can be used as a label arguments. For example, if you have define a function like A, B, C, D here, C and D, these are 2 keywords, are separated by a semicolon. Use a semicolon after the function's unlabeled arguments, and you can use this to do that. So C here will be operation. C is optional arguments because we provide a default value for it, and the D here is so-called keywords arguments. It's operational. It's optional, and it doesn't need to be in your arguments. And there is a semicolon behind it to tell you that D here is a keyword argument. So that's it. So now the trick is the key idea is the default value. If you have a default value, then at least your optional argument. If you have a semicolon here, everything behind the semicolon will be treated as a keyword arguments. as the definition, as shown in this definition of this function. Okay. In Python, if you're familiar with it, you need to define anonymous functions. In some cases, if you don't want to define a function, but you just want to define a function whenever you need it. So you don't have extra definition of function. So in Julia, you can define anonymous function without a name. For example, you can define x to x minus 1. Let me see if I can, so I can define a generic function with message. Let me see what where info. I have so many variables defined here. I have x as at bar. Okay, so it might be overlapping with my previous definition of the x variable, but never mind. I'll go back to that later. I'll make this more readable. So you can define an anonymous function, or you can define a function, like this without a name. A function x to x minus. So usually, if you don't have a name for function, there's no easy way for you to use it. So that's why you can define it, but how to use it, it's a different story. To use it, usually you use it in this kind of mapping functions. When you want to map something to something, and you don't want to redefine, define a function, you just want to define the mapping from the x, y, z to x plus y plus z. So you're trying to map three numbers to one number. That's this mapping. This is not more than a function, but you don't want to give a name. It's just for simplicity purpose. You can give it a name, it's fine. You can just define a function previously. But just in some cases, you probably just want to say, hey, I just want to do this once. I don't want to reuse it in some other cases. I don't need to define a function for it. It's fine. So you are the boss, right? So you define this, and then this mapping will take the input x, y, z as a one input and map that to a number x plus y plus z. So that's what this function is doing. You can try it out yourself, but we'll go quickly. Let's skip this one and go to the next one. So the dotted function is something really, really powerful. That's something I mentioned. If you want to define a function with x, a, f, a, b, let me do this quickly. If you want to define a function, say a and b is equals to a times b, okay. So if you do a function says 2 times 4, you'll get 8 because it's a 2 times 4. Now, if you define a variable a, let's call it something different. A is fine. Call the variable a, which is 1 and 3, 4. I know this is just arbitrary array. I have a 5-element array defined as a. I have say b equals to a. Let's just get b and a the same. So let's try to call this a and b. Oh, I forgot there. Now you'll see if you are directly call this function, because a and b are two vectors, they're not working because my function is only defined as a function for a and b to time to each other. But a and b are, they are just for numbers. I don't define a function to deal with two vectors. How to do it? So as I'm showing here, you can simply do a function dot. So what it does, it's take your function and apply and map your function to what? To every element of these two elements or two vectors. So my vector a and b, they're the same. It's like 1, 3, 5, 6, 5, right? If you multiply 1 by 1, it's 1, 9, 3 by 3. It's it's just the square of each element. So this function now it's going to be used to deal with vectors without me writing a single piece of code. I just need to worry about how I can deal with every single element, and this dot operation will automatically do the mapping for me. So what this dot did, it's just like this map function on the previous slide. So this map function is just map this whatever my func and give this input. So it's the same thing. Okay, so let me do func. Okay, let me do 1, 2. Probably I need a 2 variables. 5. Sorry, 2 method mapping. Map x, y. Map 1, 2, 3. I'm sorry, 1, 2, 3. Probably no symbols, maybe. I just want to. Okay, I'm sorry. I just because when I put everything in the parentheses, the map function will consider everything as a one single input. And of course, my function cannot take this one single input. It needs 2 input, which will be the first one and the second one. So what this one does is taking my first 1, 2, 1, 3, 5, and the second 1, 3, 5, these 2 arrays. And they use these 2 as an input for the function, but this mapping is apply this map function to every element one by one. That's what the map does. So this map is used a lot when I'm not sure for me, those of you who are familiar with the big data analysis, you have a map reduce, right? That's map exactly the same map when you're talking about map reduce. When you do the map reduce, you do the mapping. You define a function applied to a single element, and you apply your map function to all the data you have. And then it's like a data-based data parallelism. And then you do the mapping, and the function will, you run your function on all the data you have. And then next you do the reduction. So to collect the data together, do aggregation, maximum, minimum, or sum, and all those are so-called reduction operators. That's how map reduce is working, right? And this map is the same idea. You map the operation of this function to every single element, corresponding element. Of course, if, let me show you. If I define a map like this with different number of elements, how will this work? It still works, it just ignore all the extra ones. But again, if I'm writing this function, I'll give you an error message. But here, it's just ignore all the extra elements, just do whatever the minimum number of elements can match. So it's a map 1 to 1, 3 by 3, 5 by 5, but all the other 6 and 5, 2 elements will be ignored for the other one. Let's do the other way. I'm not sure if this probably working the same way or different ways. I never tried it myself, but okay, it's just ignore whichever is longest. All the extra elements will be ignored. But this dot operation, that's exactly what dot operation is about. You can define, in the same way as I'm trying to here. So dotted function is really, really powerful. You can apply this to existing functions like sine. You can show example. You can do function this, or you can do sine dot this. So what it does, it will take the element-wise operation for A and B and apply function to it, and then apply sine to it. So you're more or less like take a sine of A, each element of A times each element of B, and do this for element-wise. So you can define a functional function, which is just a nested function, nothing more, nothing less. And you can always define a functional function. And this function could be a function, another function, and could be the output of another function. So which is like a parameter you put in your lambda function, and then you can do some fancy things. I'll just skip it quickly. I don't think it's really that complicated. You can try this out yourself. So next, we'll get into the basic structures of Julian. With functions, variables, statements, we can start building up, bigger applications. And to start doing that, you want your code to be more readable. You want your code to be more organized. And the tuples, arrays, sets, dictionaries have been designed to help you on that. As you are familiar with Python, these are all the data structures used in Python. So, Julian is built on top of Python in many ways. And this syntax, all the things, we are familiar with Python, and could be directly applied to Julian programs. Like tuples, you can define tuples. Tuples are immutable. You can define tuples and tuples. You can directly visit tuples, and it's just considered like an array or a list in Python or it's just a tuple in Python, but it's like array, and you can visit each element. You can define multi-dimensional tuples, etc. And you can, define it. The only thing you need to keep in your mind, that's very important. Tuples are immutable. You cannot update or change a tuple. You can reset. You can set a tuple to a new copy a tuple to a new variable, but you cannot change all the elements in the tuple, which makes it very, very good for storing parameters and storing some information that you don't expect to change. And of course, there is always a price coming with this, and always a price coming with mutability. By making these tuples immutable, it's usually faster to retrieve the information in tuples. And this tuple structure will be less expensive, and it's usually doesn't need to store extra structures to handle any changes, any updates. So make it very efficient. So arrays is like a list. So it's nothing more than a list. It's just a list. You can do it exactly the same way. Whatever you do with Python numerical numbers, like numpys, could be easily done with the Julian. You can do the concatenation. You can do a concatenation, horizontal concatenation. You can do vertical concatenation. I'm just showing you at the bottom. You can also generate a random. You can use a 0 and a 1s. And let me show you just one quick example so that you see what I'm talking about. So I can define A as 0s, say 5. So that's, I generate 5 zeros as I'm showing here, or I can create a 5 by 5. So this is my A. I can create my B is say 3, 5. Okay. So now if you look at A and B, they have the same column. So I can do the vertical concatenation. So vertical concatenation could be done with, I'm not sure it's vertical, it's with a semicolon. So A and B, I'm sorry, put them together with, if you do A and B, this will concatenate two matrices together, create a 8 by 5, because you have first one is 5 by 5, second one is a 3 by 5. So you get a 8 by 5. But you cannot do that vertically because they have different, they don't have a matching dimension. Or you can create B, you can create this probably 5, this 6. Now this B is like this, your A is like this. You can do the horizontal concatenation. So this is a very easy way for you to deal with expand your table. You want to deal with machine learning or trying to train your models. You can easily create new features and append new data, etc. Right? And you can do others. It's just the same as a numpys and py, syntax. And of course, you can do dot operations. And we just mentioned about A here. A dot plus 10, set 10. This is what I got. Then you can A dot minus, say 5. Again, A itself is a matrix. It's a Julian matrix. And the dot operation is operating, this dot is connected with minus sign. So dot minus sign itself is operator. So what I'm trying to do here, I try to use my A matrix as my input. And then I use apply dot minus to A. So I got output this way. Okay, so the same goes for sets. It's almost identical to anything you're probably already familiar with in Python. It's just like, it needs to be unique. And everything else is just like just like a list. And you can do union and intersection and other things. You can play with this. And dictionary, it's like a key value pairs. You have, I can simply copy and paste some of the examples here. Or a dictionary, you can create a dictionary with October. I can delete and remove. You can try this directly, but you need to use a dictionary to define. So define A equals dictionary. Let's see what I had. Let's O is corresponding to, I'm sorry, it uses this different symbol. Equal. October. I'm just using this probably simplified version of this. November. So I define this two. So A, O, sorry, it should be double, I believe. Double quote because it's in, we'll give you October. It's exactly the same way the dictionary is working in other languages. And nothing more, nothing less. So last one, I think is this already getting to close to the end of the project. So the loops and the conditions, these are the fundamental building statements, blocks for program languages. For I believe 99.99% of, I'm just arbitrarily give a number, percent of program languages could be simply built with simply combine the if condition and loop condition, loop statements. Most of the stuff could be done by combining this with nested structures, and then you can get almost everything. Almost everything. I cannot say guaranteed as everything, but almost everything done with just combination of loops and condition loops and if conditional statement. And there are some controlling blocks for loop, conditional, and while, and these are for different, for if else and loop, and it has also while and the loop and a for loop. I'll show you some examples here. Do I have? Yeah. So to get into the if conditional statement, you need to understand there are some other statement for the Boolean expressions. If you have, if you define x equal to 1, okay, for the first statement, and then you want to compare if x is greater than 0 and less than 0. If greater than 0, good, I'll use the first statement, which is sine x. If less than 0, it will be cosine x in a similar way. So we can combine the Boolean and etc., put them together and build up a conditional statement that we can use. So we can use a if to tell if the conditional statement is true. If it's true, do something. Else, do something else. And you have if. You have multiple else if statement. Then you have else, which will be the default. Whichever condition cannot be satisfied, else will handle the rest conditions. So you have a complete description about all the possible conditions. Otherwise, you might be missing some conditions. So else more or less like a default catch up for everything you might missed in the previous else if conditions. So it's exactly the same structure you learned from other languages, and this will help you to dispatch all your possible conditions in a different statement, and almost everything you're dealing with scientific computing could be done by using different levels of conditional statements plus loops. Almost all the scientific computing problems you can deal with. For business logics, there might be some other things I'm not familiar with, but for most of scientific computing problems, by combining if-else statement and a conditional statement, it can cover almost 100% of your scientific computing needs. So this loop condition is just, you have an index I going from 0 to some number, you have steps. So here, if you do for I in 0, 1, 10, it's just going from 0 to 10, but with 1 as a step. You can change this step to 2, it will be increased by every 2, it will increase, I will be increased by 2 for every iteration. It will be go 0, 2, 4, 6, etc. And when you're the second loop condition is starting looping through this string with all the characters as its input. So every time you printed L, it will just print J, U, L, I, A, etc. Everyone as an individual character. So again, strings are nothing more than just arrays of characters. If you understand that, this statement is not a string to you. It should be straightforward. And there are also other for loops. You can use that for how to call these generating create a list or create arrays in Julia. You can do the array comprehension. That's the same thing we did in Python. You can use an enumeration. Enumerator will give you not only the number generated, but also the index for that. So that's what the enumerator is about. Then you can do the sum you can use for to generate input argument for other functions. Of course, usually it's nice to write code this way, but I would highly recommend you to write down each statement separately so that you have a clear understanding about what's going on. Sometimes if you put all those things together in one big statement, it's kind of harder to understand. And also you can nest your loops and you can show them separately. And the while loop, it's kind of like for loop, but when you don't know exactly, some condition might not be happening, you don't know how many iterations you want to go, you use a while loop. If you know exactly how many iterations you want to go, like 1,000 iterations, just use a for loop, which is very straightforward. While loop will check the condition first, and then do the calculation. And the for loop will always do the calculation inside this for loop. And then towards the end of the for loop, it will try to evaluate whatever the index condition to see if it satisfies a certain condition. If the index already go out of the range, your for loop will end. So while loop always do the conditional statement first, and then try to evaluate if your n is less or equal to 100 here. If it's less than equal to 100, it'll do the calculations. Otherwise, it'll just escape. Just like many other languages, you can do the try-catch. Try-catch is a very, very powerful way for you to capture any problems, mistakes you might be happening, and it's also helpful for you to debug your code. And it's a pretty common thing in C, Java, and Python, and it's nothing different here. I know we're a little bit out of the time here, but the last one will be very simple. The reason it's simple because we're not doing a lot of very complicated plotting here. For most of scientific computing, plotting is very, very important. But unfortunately, with this web-based interface, sometimes the plotting tools might not be working nicely. The very first tool I want to show you all is called a Unicode plots. And we already installed the plots function, plots module. We can what we do next, we can call Unicode plots. If you are using a prompt like what I'm doing here, Unicode plots, I think. It's not defined. I think probably I need to using plots. So I'm trying to load this plots module, and it will pre-compile all the functions I need to use. That's how Julia is running faster, because it gives you the source code as a compile it based on your hardware, make it more running native. But whenever you load this module, it's getting really slow for the very first time. After it's compiled, next time we load it, it will be much faster. So currently it's loading my plots module, and I'll be calling this Unicode plots function, and then I plot this random number, and I generated 5 rows of random numbers with 5 points each. So you can see what I'm going to do here in a second. So I loaded this, then I'll try to Unicode plots. I call this function to initialize everything I need to do the plotting. Okay, and I don't know. Okay, it's already loaded. So now it's using Unicode plots as a backend. As you can see, plots can have multiple backends. You can use Unicode plots, you can use other plots. And I'll show you one more example in a second. And then you can do plot random 5. And I have the line width here. You don't worry about it. You just do the plotting. And you can set your title, etc. I don't know why it's kind of slow here, but here it's now. Remember, this is not graphical interface. This is a purely Unicode-based plotting using my terminal, and it's like ASCII arts, right? I mean, it's plotting out the 5 lines, or if you prefer, you can make this less, probably 2 lines. I'm sorry, this is 5. This is 2. Sorry. So I have 2 lines, and each line is showing the random numbers. I just plot it out, and it's a very nice way to do the plotting. Okay, so you can try this out, but it might not be working on the web-based shell that I should you to log in on faster. But if you can log in with your terminal, this definitely will work. And I almost can guarantee that it never failed to work for the Unicode plotting on terminals. But this one might not be working if you're using that. So I'll just keep it here as an example. You can do the plotting. This needed to have a graphical user interface activated on your remote end, which might not be the case, and which probably not the case for our HPC users. But this can, if you have a Julia installed on your local system, on your computer and laptop, this could be directly run. You'll get this window, nasty window, and it will open up this HTML file, which is generated through Plotly. Plotly is a very nice package for plotting interactive plots, and Julia is supported by default. Oh, I'm sorry, it's not by default. You need to activate it using Plotly function call and switch the backend to Plotly backend. So that's how you do it. And lastly, I want to show you an example of the fractal. And this is probably the most famous example. And again, you remember the performance plot I showed you. This benchmark actually Julia can do faster, can beat C in the way how it's doing the microkernel calculation, which is pretty amazing. Probably mainly because of the way how they do the optimization in time and make things running faster. So what it does is trying to do a very simple calculation for all the points on your complex plane with Z squared plus this constant C, and generate another point and keep doing this for all the points. And then whenever the value of C is still bounded, then you output your Z, etc. So it's below certain conditions. So look at this example. So I'm trying to define a function for them called Mandelbrot, function. This function take Z, initialize Z as 0, and then iterating like 50 times. It's trying to calculate Z squared plus A and set this to Z, and keep iterating 50 times until it returns C. So this A will be the input variable, and this A could be any number I put in there. It's just the arbitrary number I put in there. So in this function, I'm trying to calculate some. I put a complex number x and y, and x is it goes from 0 or from 1. X goes from 0.5 to 2. Oh, -2 to 0.5, and y goes from 1 to -1. It doesn't matter the order. So it's just a pairs of numbers. So then I calculate my Mandelbrot complex. I use x and y to construct my A, which is a complex number. I then use a Mandelbrot function call to calculate my Z here. Then whenever my Z is less than 2, I print out a star, and if less than 2, print a star. Otherwise, print a space. So if I can copy, let me go back to this code, and let me copy and paste this function to my prompt here. So this is what I got. You can print out this star. So I'm not using any plotting tools. This is just trying to do this like line by line. For every row, I print out star and a space. Whenever this condition is satisfied, I print out a star. Otherwise, I print out a space. And I can do this line by line and finally get this shape, which is very, very beautiful. You might not agree, but it's fine. So getting back to your, HPC system, you can use a Control D to quit. I'm sorry, Control D. I'm still on faster, so I can get to Scratch. I can go to my Julia example here. I can change my, with Julia. Okay, so I can submit a job as batch Julia. I think I have this already submitted. So this should give me an output. And this output will be, what I'm trying to do here, I'm trying to run this Mandelbrot Julia function. So it will generate this figure for me. So I'm just waiting for the output here. I'm sure if it's coming. But if I go to my previous one, I believe it's already no, this one it's already expired. No, okay, good. So I go to my previous job and go to Julian examples, you should see the output here. Julian, the output from my previous job has been already dumped to this file. If you can't more or less like showing this file, it's actually print out this, the output of this file will be saved into, output of my code will be saved into this file. It's ending with my job ID, started with the name I gave in my script. So you'll get a plot like this. So this is on my exit account, but go back to my, okay, this one is also done. I can, this is on my Tamu account. So this is what this could look like, the output looks like. Okay. So again, I think that's more or less conclude what we are going to cover for today. There are many other nice features. I didn't get into the details today, but those could be very, very useful for your real world applications. For example, like MPI libraries, neural network libraries, and linear algebraic libraries, and other libraries that the Julia community is providing. And those will be very, very powerful, you know, just like a Python libraries. Those could be helpful for you to construct real world applications. With that said, I have all the online resources listed here. You can check them out. And also I'd like to thank, you know, HPRC and Institute of Data Science for the helping the support, and also the TEAS for supporting me when I was still a research scientist working at the TEAS. And this material, together with all the other extra stuff, examples and documentations, have been supported by National Science Foundation programs, and we really appreciate their support. With that, I'll consider this, I'll call the end to this short course. If you have any questions, feel free to ask me directly, or you can just send me an email. I'll be happy to help you on some of your, you know, technical questions. My email can be found on the slides. And with that, I'll say it's end for the short course.